Thanks, guys. Thank you, everybody, for being here. It's a great honor to present. As you heard, we do a lot of online education, rarely get out into the world. In fact, sometimes like days go by, I'm like, is it Saturday? Is it Wednesday? What's going on? This is pretty cool. It's been a great conference so far. We've had a good range of speakers on different topics, like the previous speakers just speaking on deep learning. What we want to do is, we're not going to present you with something awesome that we did, and we want to give you a takeaway from today. We want you to go home with a confidence that you now understand 3 of our favorite machine learning algorithms. So it won't be more about like something that we've done, it's more about you guys, so that you go home and for the rest of your life you know that you know these 3 algorithms. Specifically, we'll be talking about SVM, supported vector machines, naive Bayes classifiers, and the upper confidence bound reinforcement algorithm. So as the MC kindly pointed out, there's a little bit of information about us. We teach mostly on Udemy and other platforms as well. Do some other things, extracurricular activities. Yeah, but on that note, we're kind of like we're super pumped to bring you this, seriously, because we've had so many people give us feedback about that. These types of tutorials where we don't focus on the code. You know, you might come across, like you will see coding, but we won't be focusing on formulas. We won't be focusing on the math. We won't be focusing on the integrals, on the complicated stuff. We like take that out of the equation. We're here to show you how it works in the background, like what is happening, so you can like intuitively understand what's going on. So I'll be explaining that part, and Hadelin will be showing you an actual real-life scenario of that being applied. So without knowing like the nitty-gritty nuts and bolts of things, you'll be able to know what's going on and how to apply it in real life. And we think that's where the real value is. And then if you want to learn more about it, you can find out more in your own time. So we're pretty excited. Are you guys excited? No, I can't hear you. Are you guys excited? Yeah, let's make this happen. All right. So that's us. Oh yeah, I'm passing over to Hadelin now.
Yeah.
Here you go.
Okay.
Oh, you got the point.
So we're going to start with a simple definition, and actually it's not only simple, it's the first definition ever given about machine learning. It's that guy that brought up this machine learning term, and so it defines it as the subfield of computer science that gives computer the ability to learn without being explicitly programmed. So that's exactly what we're going to do. And then now a more nowadays question is that where do we locate machine learning in all the terms, deep learning, machine learning, artificial intelligence? Well, you know, for some people that's the same. For us, our vision is that artificial intelligence is the big thing. Like it can be, you know, to train some bad guys in some video games. It can be machine learning. So machine learning is to us a branch of artificial intelligence, and actually this is the most powerful branch. And then if we want to go deeper, like to solve more complex problems, then we have deep learning, which is based on neural networks that mimic the processes of the brain. So that's our vision, and you'll see that we're going to start with machine learning, and if you want to go deeper to the next level, you go to deep learning. All right, then it's important to have a structure in all this maze, machine learning maze, because machine learning is really broad, and we structured it in all its branches, because machine learning can perform multiple tasks, and we're going to see each of these tasks. So the first one is regression, and it's when you want to predict a continuous outcome. So for example, you want to predict a salary. Then we have classification, when you want to predict, for example, the winner of the next Super Bowl, because you're trying to predict a category. Then we have clustering. It's actually funny, this one, because you don't know what you're looking for. So you're trying to identify some segments, some clusters, we call it clusters, in some data that is impossible to detect anything at the beginning. Then we have association rule learning. So maybe some of you have already heard the term market basket analysis. Well, that's basically, you know, you saw on these websites like Amazon, people who bought also bought. Well, that's what association rule learning is about. You know, you're starting from something and you're trying to predict the next action. Then we have reinforcement learning. So that is the branch of machine learning the closest to artificial intelligence, because it's with reinforcement learning mainly that you're going to build some robots. So Kirill is going to talk about it, like robot dogs, for example. And then natural language processing. Of course, you've already heard about this. This is machine learning with text. So for example, that can be a And also speech, by the way, speech recognition and sentiment analysis, for example, to predict if a review is positive or negative. That's the classic example, but of course, there is amazing applications in natural language processing. And finally, deep learning. Deep learning, the most powerful branch of machine learning that can solve the most complex problems nowadays. And okay, so we're going to work with some data sets today, 2 data sets. These data sets are available on the Super Data Science website at this address. And so feel free to check them out. You also have the code templates, by the way. All right.
Thanks. So I'll just click back because I can see a lot of you taking photos. If you want to take a photo, go ahead. While you guys are doing that, I forgot to ask completely at the start, who in the audience has done at least one of our courses? Put your hand up, please. 1, 2, 3, wow, okay, 5, 6, 7. It looks like, whoa, that's really cool. We're expecting 2 people. We've met actually 2. It's really cool to meet you guys live. So just for the benefit of you guys, this stuff is coming from our machine learning course, so you might find it repetitive, but it's always good to kind of reiterate things. And with that in mind, let's get started. All right, so we're going to talk about support vector machines. Sounds pretty complex, doesn't it? Support vector and some machines going on in there. Actually, it's very simple. Everything's very simple. It's when you break it down, it's all simple. So we're going to be looking at apples and oranges. How does a machine understand what's an apple, what's an orange? And you probably know there's lots of different ways that this can happen. This is a classification problem, so you know what, you have 2 classes, you have apples and oranges, and then you have your new object, and the machine has to identify, based on prior experience, is this an apple or is this an orange? And you probably heard of KNN, K-nearest neighbors, or you've heard of CNN, convolutional neural networks in deep learning. So support vector machines also address that problem, but a bit differently, and we're going to talk about that. So let's say you have those 2 classes there, and to make it easier, we're going to actually look to kind of like make it more realistic. We're going to, for starters, we're going to look at how we're going to separate them. So the goal is to put this boundary between them so that we instantly know when we have a new data point based on x1 and x2, is it category A or category B? Is it an apple, is it an orange, or is it something, one of the 2 categories that you're selecting from? So how do we select that boundary? Do we select like that? Do we select like that? How does the machine know where the boundary is? So there's, as you can see, there's lots of different boundaries that you can possibly choose from. And here, this is how the support vector machine actually works. It selects a boundary where you have, it looks at the 2 points that are nearest to each other. And it maximizes the distance. So you can see those perpendicular lines from the points to the horizontal to the long line. That's the distance, so it maximizes that margin. That's called the margin. And here you can see those 2 are the support vector machines. Those are the support vectors. And why are they called support vectors? Simply because as we know, in mathematics and everything, all these points in a multi-dimensional space are actually vectors. They're not just like coordinates. Like you can call them coordinates, but in a multi-dimensional space, it's easier to call them vectors. So that's why it's called support vector machine, because that line is built based on those 2 vectors or 2 points. So we've got a couple of other terms here. We've got the maximum margin hyperplane. You might hear that term. We've got the positive hyperplane. We've got the negative hyperplane. So all of that is mathematics, and we promise to stay away from that. We're going to get to the essence now. So why is SVM so cool? Why is it so different? So draw a line. A lot of algorithms can do that. So what's so special about SVMs? Well, back to our example of oranges and apples. Let's have a look at what's going on here. You've got the line. If we think about it, we want to separate apples from oranges, right? So the red ones are apples, green ones are oranges. We want to know where's that decision boundary. So when we get a new point, is it going to be an apple or an orange? We have to be able to tell instantly just by looking where it falls on the plot. So what normally algorithms would do, like KNN or CNN. So you've heard these problems that like a machine, algorithm can look at pictures of dogs and cats and can understand if it's a dog or a cat. Well, that's the same problem. So what they would normally do is they would look at the most aptly apples and learn from that what an apple is or a cat is or whatever it is. And they'd look at the most orangey oranges far away from the boundary, deep inside the kingdom of oranges, and they would understand what an orange looks like. But what an SVM does, it's goes radical. It's like, I don't care about any of that. I'm just going to look at the most orangey apple, this one. I'm going to look at the most aptly orange, that one. So whatever is like the most extreme type of apple that is most similar to an orange, and the most extreme type of orange similar to an apple, I'm going to look at them, and I'm going to actually build my decision boundary based on that. So those 2 points there, that's your most orangey apple, the yellow apple, and that's your most orangey, appley orange. And therefore, the SVM is so different to all other algorithms that you know, like KNN or CNN and others, that it like radicalizes this process, and therefore you can get some amazing results from SVMs. Like some cases they work much better, some cases they work much worse. So it's always good to have this in your arsenal and to remember that if you can't classify something with a standard classifier, you might want to look at SVMs because they radicalize this process. They don't really care what's going on in the kingdom of apples, in the kingdom of oranges. They just look at the most extreme cases, put the line straight between them, maximize the margins. You got your positive, negative hyperplane. That's all you need to know about SVM in order to be able to know in which case you might want to apply something like this in your work. So that's the intuition behind SVM, very quick and easy. And we're going to proceed to the practical. So Hadelin will take over here. One of the reasons why we're kind of like rushing a bit through this because we've got 3 algorithms we want to show you. And it's going to take some time. So Mitch, how do we get the code up? Yeah, no, code's not up. Sorry, guys.
We want to have this.
It's not powerful.
No.
Yep. Let's see. Minimize this. Here.
So while they're fixing that, does that make sense, guys? Yeah? Okay, I see some nodding, some people nodding. All right, that's good. Question, yeah?
Would you ever start SVM?
Yeah, it's totally up to you. Like it depends on the problem. If like a KNN or a CNN is like a standard approach, I guess. Like I wouldn't say that as SVM or KNN. Like KNN is probably the easier approach. CNN is deep learning if you're doing deep learning. For me personally, SVM is kind of like a fallback approach if you feel that you're not getting the right results with the standard ones. SVM can be a better bet because it approaches it so differently. Thanks for the question.
Okay,
All good?
All good, yeah. So we have a cool mission ahead of us. Think of your favorite car, and let's imagine that this car, the car company, has just launched its brand new luxury SUV car at a ridiculously low price. And our mission is to sell as many cars as possible. So we can imagine we work for this company or we're at the board, but we have to sell the maximum cars. And so we're going to take 2 ways to do this. We're going to optimize 2 things. First, we're going to target the right customers to sell the cars. And we're going to use a data set, and we're going to do this with a classification model, which is SVM, and then the next one. And then what we're going to optimize is the ad that we're going to show to the social network, because of course we're going to use digital marketing. So we're going to show some ads on social networks, and we have a couple of ads, and we would like to know which ad will sell the best. So let's start with our first way with our SVM. So, okay, we have this code. It can be impressive, but you'll see that it's no big deal. We have different code sections. Basically, we can divide it in 3 parts. The first part, coming from here to the top, is the data preprocessing phase. Every machine learning model has a data preprocessing phase. That's what's most important. You have probably heard of the 80%, 20% phase. Well, 80% goes for data preprocessing. That takes a lot of time. And basically what we do in this phase is that we import a data set. We split the data set into a training set and a test set. So the training set is where the model will learn the correlations, and the test set is where we will test its performance on new observations, like testing the predictive power of the model. And then we have feature scaling. That's what we have to do to make sure that all the variables are on the same scale, and therefore to make sure that no variable dominates another variable. Okay, so that's the first phase. Then we have the second phase, which is this one. And that's where all the magic described by Kirill happens, all the magic with the apples and oranges. So this is where the training will be done. And once the training is done, we will visualize our results, and you will see where the customers are targeted, mainly, and where the customers are predicted to buy the SUV. Okay, so first what we're going to do is import the data set. So just executing, and here's the data set. So as you can see, we have five columns. We have the user IDs, so that's the user IDs of all the users in the social network. And then we have some features like the gender, the age, and the estimated salary. So that's the features that we're going to use to try to understand some correlations between these features and the decision of the user to click on the ad to buy yes or no the SUV. And speaking of this, that's the last column. The purchase column takes a binary value, 0 and 1. 0 means that the user didn't buy the SUV, and 1 means that the user bought the SUV. And so from all these data sets, from all the data in this data set, we're going to try to learn some correlations. Well, the SVM is going to try to learn some correlations and classify the users whether they're going to buy yes or no the SUV. So of course, in real life, you have much more features, but I'm choosing this small data set so that we can visualize this in the end on a 2D map. All right, so now time for training. I'm going to restart. We're going to do the training right now, so that's where all the magic will happen, and that's where all the correlations will be learned. And then we'll get to the most exciting part. We will visualize the results, and we will see where is the main target. By the way, the software that I'm using is Spider, and for those of you who want to begin in machine learning, I recommend Spider because it's like a studio, very intuitive. Okay, here we go. So I'm going to take care of the data preprocessing phase again. All right. So the training, I'm doing it with scikit-learn. That's the most efficient way to train a model these days, simple machine learning models. And as you can see, this takes 3 lines of code, so that's pretty cool. I'm basically creating a classifier, and I'm using this SVC class, which is the class that contains the SVM and SVR model. And I just need to execute. And here we go. We have our SVM model. So we have already learned all the correlations. It is trained. And now we're ready to make the predictions. So I'm going to make the predictions at the same time as visualizing the training set results. So that's actually the next 2 sections. So in this section, for example, this will visualize the training set results. So that means that we're going to take all the users of the training set, and we're going to predict if they bought yes or no the SUV. And so what we're going to do is we will compare the predictions to the actual results, the real results. And so when I execute this, look at what happens. We get this map. So there are 4 things to understand in this map. You see some red dots, some green points, red region, and a green region. So the red points are the actual users that didn't buy the SUV in reality. The green points are the users that bought the SUV in reality. Then the red region is where the model predicts that the users don't buy the SUV. And the green region is where the model predicts that the users buy the SUV. So that's pretty good predictions because you can see that most of the red points are in the red region and most of the green points are in the green region. However, we can see a problem here, is that, okay, so I have to show you. Here we can see some green points, and they fall in the red region. And that's some points that the model couldn't classify properly because actually this is a straight line. And why is it a straight line? It's because, for a specific reason, it's because the SVM is a linear model. So because it's a straight line, it cannot catch those users in the right region and those guys here also. So that corresponds, by the way, to users who are older and have a low estimated salary, but they still bought the SUV. And those users are younger, but have a high estimated salary and that buy the SUV. So now the challenge is that we need to improve the model and make a model that will make some kind of a curve to be able to catch those green users here in the right region. And that's what naive Bayes will be about.
Okay, so yeah, if you can bring up the presentation. Yeah, so that's an example of like a lot of the time machine learning sounds scary and sounds like there's a lot you have to learn. You have to like sit and spend weeks before or years before you can apply. No, All you have to do is that, and understand the intuition behind things, understand the code, or even just use the templates. I think that's totally fine as well, as long as you drive business value, right? Like we had some speakers talking about business value. That's what you have to drive. So if you can drive business value with just using code templates and using them correctly, well, why not? And then you can learn as you practice. Practice makes perfect. You learn the rest of the stuff as well. Great example. We're going to, so Hadelin will continue with that example in the practical, but for now we're going to look at the intuition behind naive Bayes classifiers. We're kind of going like okay on time, which is great. Yeah, so okay, off we go. This is going to be fun. It like actually feels that we've got 3 presentations in one, and it's good that we get like, okay, now we're warmed up. Okay, now it's going to go better. All right. Bayes' theorem. So who knows Bayes' theorem here? Hands up, please. Ooh, wow. Okay, educated crowd. Great. So let's do a mental exercise. Love these. Let's say you're walking down the streets of some university. I'm not gonna name it. You guys know it. we went visited it just recently. But you're walking down the street of some university. By the way, this is not my example. This is a great example I saw from one lady on the internet. Forgot the name, but amazing example. Really made it click for me what Bayes' theorem is. So it's like Bayes' theorem in 5 minutes. So you're walking down the street of this, or the lawn of this university, and you bump into one of the students there. And you chat to them for like 3 minutes, 5 minutes, and you realize that they're very shy. They're a very shy person. What would you say that they are? Like, what do you think they're studying? If you only have 2 choices, they're a PhD in mathematics, or they're from the business school. Like, you only have those 2 choices, and you've been chatting to them for 5 minutes, and you can see that very, very shy. So, who thinks that this person is a PhD in mathematics? Hands up. Beautiful. Who thinks this is a business-savvy, aggressive type of person? You know, smashes it on Wall Street. Okay, great. 5 people put their hand up. So now let's go through why most of you guys are wrong here. So the situation is we're assuming through that thinking process that you went through, even though so many of you put your hand up that you know Bayes' theorem. Like Bayes' theorem is great because you can actually apply it in life. Great book about it is The Signal and the Noise by Nate Silver. Haven't read that? Read it. Best book on Bayes' theorem and frequency statistics. Amazing. So the assumption that you made just there was that these probabilities are equal. And so let's go through these. What is that? That is the probability I asked you about. So you know that they're shy. The question is, are they math? So are they math if they're shy? What's the probability of that? The probability that you already know is that they're shy if math. So you know that people who do math, you know, like most of the time shy. Like PhD in mathematics, it's not a world secret that probably like 75% of people who do PhD in mathematics might be shy. So that's the knowledge you have, and you assume that these 2 are equal, and therefore you came to the wrong conclusion. If you apply Bayes' theorem, you won't have that problem. How do you apply Bayes' theorem? Well, that's not equal. Bayes' theorem is basically this. So there's a little adjustment you have to do, and we're going to go through this right now. We've got like 2 more minutes for this. And then in the naive Bayes classifier, it'll be like super obvious. So what are these 2 things? So we already named the 2. So the left one was math if shy, and the second one is shy if math. And the best way I find myself, best way I understand the Bayes' theorem is like if I multiply the bottom part by 1,000 and the top by 1,000, that's like, let's say there's 1,000 people in this whole university, and that changes it from probabilities to actual numbers. So what you have at the bottom now, all of a sudden, is the total number of shy students. So let's remember, B is shy, A is mathematics. So you have the total number of shy students in the university, right? Like, so logically, how do we calculate? Okay, so that's the total number of shy students. Now at the top here, you have the total number of math students in that university, regardless of whether they're shy or not. When you divide one by the other, all of a sudden you have the percentage of math students among shy people. Like, that makes sense, right? That you just divide one number by the other. This is like logical if you don't look at the rest of the formula. But now what happens is now you can plug in those values that you already knew, because it makes sense to multiply shy if math by the percentage of people who do math, because the thing on the right is actually the percentage of people who do math. So you might multiply that by shy if math, and you will get math if shy. So you will get the probability of somebody doing math if they're shy. And it turns out that why you might be wrong is, well, you probably are wrong, is because you're not taking into account your prior knowledge. So this formula and the whole concept of Bayes' theorem takes into account your prior knowledge. And your prior knowledge might be something like this, that this is your total 1,000, and total whatever number of students you have at the university. Well, the number of people studying math PhD is at the top there. That's total math students, and that's your total business students. So even though what you knew before, that 75% of people studying math are shy, even if 15% of people studying business are shy, there's still more shy businessmen than shy mathematicians, just because there's this prior knowledge. So that's the whole concept behind Bayes' theorem. You're taking into account prior knowledge. That's how it applies. Really cool to apply in life. That book has great examples about, like, if if your girlfriend finds underwear in your wardrobe that are another girl's, why she should not assume that you're cheating. It's like, it's ridiculous. It's really fun. Yeah, so Bayes' theorem applies to those. And all those false positives in medicine, false negatives, really good to apply to that. It's like kind of like the opposite of frequency statistics that we use for p-values and so on. Big like war between the two. Like real math war. Anyway, so naive Bayes classifiers, intuition. So now we're moving on to the actual machine learning algorithm that leverages this really cool principle. So let's say you have two categories that you want to decide between. And to make it like realistic, we're going to plump in some names here. So that's the salary of the person, that's their age, that's if they walk to work, that's if they drive to work, and drive is green because apparently walking is bad. Anyway, so, and then you add a new data point into this data set. So you find like a new person enters the company or whatever, you know their age, their salary, and the goal of the algorithm is to classify them whether they walk to work or drive to work without actually knowing what the real case is in their life. And so how would it go about that? Well, this is our plan of attack. This is actually quite a long one, so bear with me, but it's after you know the Bayes theorem, it should make sense. So here's the Bayes theorem, we're going to apply that. We're going to calculate, step one, we're going to calculate the probability that they walk given the parameters we know about them, their age and their salary. And we're going to apply that formula. Then, so that vertical line actually means given. So that one over there is the prior probability. We're going to calculate first. That's your marginal likelihood, calculate second. That's your likelihood, we'll calculate third. They all have names, but you don't really need to know this to apply this. Posterior probability, and then we'll get that posterior probability. Same thing, we'll calculate the probability that they drive given the parameters we know about them. Blah, 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 same thing. And then we'll compare the two, and based on that, we'll be able to choose. And this is a kind of like a short excursus into a world of machine learning where this is a probabilistic classifier. So you calculate probabilities for one thing, for another thing, whichever has the best probability. It's like a voting mechanism. Whichever has the biggest probability, that's the one that wins. It's not that it's 100%, but it's like the probability of them walking is higher or driving is higher. So ready? Let's go. First thing, okay, we've got that new point, there it is. How do we calculate the probability that they walk? Well, not knowing anything about them, that's what it means. How do we calculate is probability that the number of walkers in your whole organization or in this whole scatter plot divided by total number of observations, 10 over 30. There's 40 total, 10 people walk, no, there's 30 total, and 10 people walk, 20 drive. So that's 10 over 30, that's easy. That's gonna be like your first part over there. And the second one we're going to be calculating is the probability of actually having the parameters that they have. The age and the, so we've calculated that, calculating this one now. The age and the salary. And what that means is the way that you need to understand this algorithm without like having to go into the code and all the thing, just draw a circle. Draw a circle around that value and say, okay, so what's the, we're going to say that anybody in that region, that Euclidean region of that, around that point, has the same parameters as this person. So they have about the same age, about the same salary. So now we're going to calculate based on that. So there we have 4 points in there. And the probability of X, of like being similar to that person. So this is, if you remember in our calculation, what we had at the bottom, right? What did we have? The total number of, I think it was shy students overall. So what's the probability of just generally being shy? In this case, it's probability of actually being like that person. You just calculate it, so you have only 4 people in there, divided by the total number of 30, you get 40 over 30. So that's us calculating that one, second one. Now we just have to calculate the likelihood, likelihood, do a circle again. Likelihood is, if you look at it here, likelihood is like, what is the probability of having those parameters X, the values X that we're looking for, given that we know they're walking. So if we know they're walking, that means they're a red point. So draw the circle again. the red point, what are the probabilities of, if we knew that they're 100% walking, what would be the likelihood of them ending up in that circle be? Well, we only have 3 red points in there out of 10, so the likelihood is 3 over 10. Simple as that. Now we know that. Now it's easy to calculate the posterior probability, plug all those in. 0.75 is the probability that they walk, given the parameters we know about them. Step 1 done. Calculate, same calculations for what's the probability of them driving, knowing what we know about them. 0.25. You could have told that is the case already, right? Because like it has to add up to 1 because you know the parameters about them. There's only 2 options. So 0.75 greater than 0.25, and that means the probability of walking is greater than driving. Yeah. So what's next? Yeah. So you can see it's all kind of like very intuitive because you're just operating in that region where they are and just applying the Bayes theorem. I know it might be a lot to take in the first time, but if you go through this a couple of times, it makes total sense. Like very similar to the example of the mathematician. Can we do questions at the end? Just keep them to the end, and because we've got another one to go through. And so in this case, we're going to classify this new data point as red, as a person walks to work. And that's pretty much how the naive Bayes works. And now Hadelin will show you this in practice. We're actually going to apply it to the same problem, so it'll be fun.
Yes, exact same problem, exact same data set. So remember the challenge is to catch the right users that fell in the wrong region with the SVM because it was a linear classifier. All right, so I'm going to restart the kernel. That means that we're going to start from scratch. That's important to make sure that everything is...
We were creating a campaign on deep learning, project, course on deep learning. The amount of times I heard I'm going to restart the kernel just got ridiculous. Like, so if you're watching this on video, like I suggest a drinking game. Or every time he says, I'm going to restart the kernel, drink.
I'll try not to say it too much.
Favorite thing to do.
All right, so naive Bayes. Okay, so that's exactly the same. As you notice, we have the exact same data preprocessing phase. So we are importing the data set here and splitting the data set into a training set and test set, feature scaling, so that's exactly the same. Then, okay, we're going to fit naive Bayes to the training set. Of course, it's not the same, but as you can see, it's the same structure. We start by importing the class that's going to do the magic, which is the Gaussian NB. And then we create what we call an object from this class, which will be our classifier. And then we fit it to the training set. The training set, which is composed of xtrain, the features, and ytrain, the dependent variable. That is the result, whether the user buys yes or no the SUV. All right, so let's do this, and let's see if we get better prediction, that is better prediction regions that catch the right users. So first, as usual, the data preprocessing phase, perfect. Then let's get our classifier with these 3 lines of code here. Here we go. Now we have our naive Bayes classifier. As you can see, it's very easy. And now let's visualize the training set results, and let's hope that we don't get a straight line. And let's go that we get some kind of a curve that will classify better than previously the users in the social network. All right, so let's do this. Executing. It's ready, and here it is. So now, as you can see, very clearly, before we had the straight lines that made these green users here in the red region, so that was not OK. It was a wrong classification. But now, thanks to this curve here, the older people that has a low estimated salary are now predicted to buy the SUV, which is what happened in reality. But, and same for, oh no, here we can do better at the top left. Actually, there is going to be a bonus next to that. I'm going to show you very quickly a better model that will even catch these users on the top left, these green users. And, but as you can see, this is much better than before. We get this curve now that makes it a better classification. And so the thing to remember here is that when the data is not linearly structured, well, nonlinear model is more better adapted because, as you can see, the classification is better. But, however, I didn't remind that for SVM, this is a training set. So this is where the model learned the correlations. So of course, it tried to fit to this training set. But what would happen for new observations? We actually have a test set which contains new observations on which the model wasn't trained. So we must make sure that the model classifies well the data, even for new observations. And that's what we're going to make sure right now with the test set. So Okay, so basically this code section here was to visualize the training set result, and the code section below is the exact same code, but to do the same on the test set, so the test set observations. And as you can see, the only thing that changed is this line here. X set, Y set equals X test, Y test. That's the observations of the test set. And before we had X train and Y train. That was the observations on the training set. So basically, we're going to get the exact same chart, but this time with the observations of the test set. So we have to make sure that our model did well on these new observations. All right, so I'm going to execute this code section. And here it is. Okay, no, I have to restart the kernel now. Because
Drink.
See, you see why it's important to restart the kernel. It's because
Not important.
Okay, so let's restart the kernel. Sorry, I said it again. And so what I'm going to do is I'm going to do the data preprocessing very quickly, and then just visualize the test set results, but not visualizing the train set results. Okay. Here we go, and now visualizing the test set results. There we go. Okay, so that's the test set, and let's see if we have good predictions. So that's the same thing. Of course, that's the same prediction boundary. That doesn't change whether it's the training set or the test set, because that's the result of the model. But then what changes is now the observations, the new users on which the model wasn't trained. So that's the same structure. We have most of the users that are young with a low estimated salary that didn't buy the SUV, and the same kind of people here were older and low estimated salary, and well, here we don't have much. But the predictions are still good. The model is catching the right users even for new observations. So that means that it wasn't overfitted to the training set in such a way that it makes some poor predictions on new observations. That's not the case. So here we have some good predictions for new observations. And now the bonus, remember that for the training set, the guys on the upper left were not that well classified. So what we're going to do now is, of course, restart the kernel. And then we're going to do what we call a kernel SVM, which is a kernelized version of the SVM, which will make the SVM nonlinear. And therefore, we'll get a curve, but an even better curve than the naive Bayes.
While he's restarting the kernel, drink. I'm going to just mention this type of SVM, the kernel SVM, is pretty cool. Like it's more advanced, but if you want to ever read about something cool, it like takes your data, pulls it into a new dimension, does an SVM there, and then plunges it back into your original dimension. So it's actually really cool when you, like I think I read a paper about it on how it works. Really fascinating. So if you ever want to check it out.
Yeah. Okay, so very quickly, let's do the data preprocessing phase. I'm just executing all this section. And now, you're going to see that it's very, very, very simple to go from a linear SVM, well, SVM, we call it SVM the classic way, to a kernel SVM. As you can see, the SVC class that we use to make all the magic happen from the SVM contains some parameters. First parameter is kernel, and that's where we will choose it to be a classic SVM or a kernel SVM. And as you can see, the kernel I chose here, which I think is the default kernel, is a linear kernel. So an SVM with a linear kernel is a classic SVM as we know it. But then if I want to make a kernel SVM that is a nonlinear model, well, I simply need to change the parameter here and put RBF. We can actually have some info about the class. SVC, as you can see, it contains several parameters. And, oh, actually, the default parameter for the kernel is RBF. So my bad, but here we go. We're ready to get this kernel SVM model, which you will see will make an even better curve than the naive Bayes. So let's do it. Let's fit the kernel SVM to the training set. And now let's visualize the training set results. We're going to get a curve, because it's a nonlinear model, definitely, but an even better curve than previously. The previous curve was totally smooth, and now you're going to see that there are going to be some kind of like convex, concave curves. So you're going to see, let's do it. Executing the training set results, and there we go. Training set results. So now, let's see. Okay, those green users here now, definitely well caught in the right region, the green region, so that's good predictions. And what about those green users here? Well, now it's even better. Before, remember the naive Bayes couldn't catch them in the right region. Now they're in the right region, that is the green region. So now we must have a very good accuracy on the results. We can check that with the confusion matrix. But the kernel SVM is definitely the best model for this nonlinear problem. So here we go. That's the first challenge done. We managed to find the right target of our customers. And now we have the new challenge, which is to find the best ad to show to the customers on the social network. And we're going to do this with a very cool application of reinforcement learning, which is the UCBM, which Kirill will talk to you about right now.
Yep, so moving on to UCBM. So just quickly, this is a new branch of, a different branch of machine learning. Like we talked about classification just now, so both SVM and naive Bayes and kernel SVM, they're all classifiers. We're actually now moving on to a new branch. As you saw in the start, we had 7 branches. This one's called reinforcement learning, and it's really cool. So give it a second.
Yeah.
No,
almost.
further down. So this is a really cool branch of machine learning because I personally like it a lot, and UCB, upper confidence bound, is one of my favorite algorithms because the way it just works, and this is the way that you should probably think about artificial intelligence as well. It's kind of like a little intro into artificial intelligence. There's a algorithm in artificial intelligence in deep learning called deep Q learning, which is kind of similar to what we're going to be discussing. So it's also going to be a little segue into that if you ever want to explore deep learning and artificial intelligence. And yeah, so we're going to be talking about the multi-arm bandit problem. But before we do that, I just wanted to mention what reinforcement learning is all about. It's like if you have a robot dog, how can you teach it to walk? You can be like, okay, so take your right foot, move it forward, move your back left foot forward, and so on. Just kind of put the algorithm, if this, then that type of thing. Specifically code it to do certain actions. And that's how it'll learn to work. And that's how the world has been previously. But now what we're entering, the era we're entering now, is where you teach machines to teach themselves. So you basically create a structure within the robot dog, and you say, okay, so if you, these are all the set of actions you can do. You can move this foot, you can move your tail, you can move your head, all these things you can do. If you move a step forward, you get a candy. If you fall over, you get a punishment. But in the world of AI, you don't have to give them candy like a real dog. You know how you train a real dog? You give it, treats, and and then you tell it a bad dog if it does something bad. You don't have to do that. You just give it a 1 or a 0. So it's cheap. So the same thing here. So you kind of code that logic in, and it just does all these random actions and tries to walk, and then it's like, oh, I made a step forward. I got a 1. That's cool. I'm going to do more of that. And then I fell, oh, I'm going to do less of that. And slowly, you give it some time, but this is why we do iterations. As you'll see, that's why you do iterations. Through these iterations, it learns the set of steps that give it the maximum, maximize their, basically, what they want, the reward, that maximizes the reward. And they learn to do that and not do the bad things. And yeah, that's how you can train robot dogs. And in fact, you can train robot dogs. It's funny, you can train them to walk better than normal dogs because they come up, you know how machines sometimes come up with these weird things that you would never think of, and just you can train them how to play soccer and stuff like that. You can't train a normal dog to play soccer. So that's the power of reinforcement learning. And kind of when you're seeing artificial intelligence, that's what's going on in the background. It's not coded in most of the time. What it has to do, AlphaGo, IBM Watson, it's more machine learning kind of coded in. But AlphaGo is more reinforcement learning. It's all right, I'm going to observe these things. Okay, I'm going to learn through that. It's not coded what to do. So that's the whole area of reinforcement learning, which spans across machine learning and deep learning and artificial intelligence. And today we're talking about a really cool problem. So I don't advocate gambling. We don't advocate gambling. And this is not for you to go and try out in the casino. This is just an example, just to clarify. In Australia, by the way, from Australia, Hadelin's from France, very, very strict on these things. When you're presenting to people, make sure not to tell them to go gambling. So don't go gambling. So this is a one-armed bandit. And it's called a one-armed bandit because it rips you off all your money. And that arm is what you pull to get the thing moving. So that's the one-armed bandit problem, is when we're going to be discussing how do we kind of if hypothetically we go to a casino, how do we maximize our return? There's a lot of them. How do you maximize return? Because you have, which one do you play? And what we're going to assume here, the way we're going to structure this problem, is we're going to assume that each one of them has an underlying distribution at which it gives you out your rewards. You know, their distributions are different, but they're all fixed. It's not just like adaptable. Distributions, it's a fixed distribution, and every time you pull the lever, you get a value from that distribution that you get in your pocket, or whatever the return is from that the game you play. And so our goal is going to be, in the multi-arm bandit problem, you might have heard of this, the goal is to find the bandit, or the one-arm bandit with the highest return, and then exploit it. Exploit it as much as you can. Just one of them is the winning bandit, but we don't know which one. So how do we find the winning one very efficiently, very quickly? Like, probably the easiest thing you can do is just play each one 1,000 times. Okay, good. You know which one is the best one, you play that one. But that's called an A/B test, and that loses you a lot of money, because we'll see what the real-world application of this is later. That's like very inefficient. The A/B testing is exploration. We want to combine exploration and exploitation. We want to, while we're finding out which one's the best one, we want to start making money. So we don't want to wait until the end of the experiment. And so let's say these are the underlying distributions. So this is like kind of like a crystal ball. You see the distributions. In reality, of course, you don't know them. So from this, which one do you think is the best one that you should go and play? All right, who thinks it's number 5? Oh, sorry, yeah, my bad. So here you've got, these are just distributions. So X is the return, which you're going to get, and that's how the return is distributed. So the white vertical line is the mean of the mean that you will get, and the Y is how frequently you will get it. So basically, that's where the values will be coming from. Okay, so which one do you think has the best possible return? Who thinks it's number 5? Yes, thank you. So number 5 has the best return. So as you can see, just look at where the vertical line is, and you can see that the yellow one has the highest vertical line, and it's the narrowest around it, so that most of the time when you pull the lever, you're going to get a value very close to whatever it is, like $52. Every time you're going to get a value very close to $52. The rest, you'll get a lower value or with a higher spread. So these are just distributions of your return. So if you knew this, you would go for the 5th one-arm bandit problem. But you don't know this. So how do we find us out? And this is where the upper confidence bound algorithm comes in. Very similar to Thompson sampling. We were going to talk about Thompson sampling, but it's better to start with UCB and then Thompson sampling. Whenever you look it up, it'll be very easy for you to understand Thompson sampling from there. So there we go. That's our 5 bandits. What are we going to do? That's our distributions. Distributions again. So what are we going to do? We're going to plot these averages. So these averages that you saw here, the white lines, we're going to plot them on a vertical scale. So on the vertical line there. So there's the blue one, purple, pink, green, yellow. And again, we don't know this. And we're going to assume a starting point. So this red dot is the starting point. We're going to assume that is like our investigated average that we get from each machine. We don't know what it is because we haven't even tried it out. We're going to assume that's what it is. And those bounds, those are your confidence bounds. So the way this algorithm works is it sets an average, it says the red line, and it says, okay, with a very high degree of confidence, like a 95 degree of confidence, I am sure that the actual true average is somewhere in here. And I'm going to look for it. So it's like a search and destroy type of algorithm. And so what are we going to do? We're going to pull these levers, and the green arrow is going to tell us what we're pulling. So at the start, we don't have any data. We're going to just pull one of them. We pull that one, and what happens is, okay, so because the true average is lower than the red line, the red line is going to go down. So we got a data point which shows us, okay, the is going to be somewhere near the true average, because that's how distributions work. When you pull the lever, you're going to get a value near the true average. It's going to go down, and because you have a new data point, your number of observations increased, so your actual bounds are going to decrease because you're more confident of where it is. So now you're going to just pull another one. Okay, so here it goes up, and then the bounds decrease. Pull another one. You do this randomly at the start. Okay, so now it might go like, as you can see, it went away from the blue line, but that happens. It can randomly happen that it moves away from the blue line because you got a value, not exactly at the average. Moves up, and because you got a new value, every time you increase your observations, the confidence bounds decrease. Then you look for the next one. Okay, this time you pull it, goes down, closer to the purple, to the true average, the bounds decrease again. And why this algorithm is called upper confidence bound is after a couple of iterations, you will see that the top confidence bounds have all different levels. So from here on, you start just pulling the one with the highest confidence bound because you think that that is the best one. So here we think right now that the yellow one is the best one because it has the highest confidence bound, and we know that the true average is somewhere in that gray area. We don't know where, but somewhere there. So we're going to bet on the yellow one. So you pull the yellow one, goes up because you got a value there. And because, again, you have more observations, the confidence bound shrinks. And now you select the highest confidence bound. It's, again, the yellow one. You pull that, and it goes up, and it shrinks again. Of course, it's not going to shrink that much in reality, but this is just to illustrate the point that as it shrinks, you might actually move away from the yellow one. Now, all of a sudden, the blue one, the first machine, is the best one. Now, again, you pull it, goes down, the confidence bound decreases. It's no longer the best one. Okay, so what's the best one? The green one. All right, pull it, goes up, because, again, it could move away from the green because you randomly got a good value. It's not always going to be exactly on the mean. There it goes up, confidence bound decreases. Okay, so what's the best one? Yellow. Again, pull it. So you can see what's going on. We're getting closer and closer to the actual true means of those distributions as this happens. Okay, pull that one again. All right, as we get more data, more information, we get closer and closer. These confidence bounds decrease. And as you can see here, we were exploiting the most important, the best one, the yellow one, but all of a sudden the confidence bound shrunk so much that now we're moving on to this one again because now we think this one's the best one. And we pull that again. Oh, no, it goes down. Okay, and the confidence bound decrease. Oh, okay, definitely not that one. Go back to the yellow one. And as you can see from here on, whatever happens, the yellow one's going to be the dominant one. And you can see that the other ones, we explored them a little bit, but we don't even know what the average is. So this is very different to an A/B test. In an A/B test, you're going to just like hard power through it until you know what the average return is, until you know where those lines are, then you're going to pick the best one. Here, we've found the best one without having to explore those to the final stage. And that is the power of this algorithm. And it allows you to combine exploration and exploitation. So you exploit during the exploration, but also you get to the full exploitation phase much faster than in just the A/B test or whatever else you were going to be using. And there's a reason, so it just keeps going like that, like crazy. Yeah, there we go. So the reason why we were talking about A/B tests, because this is so powerful. You just apply it in advertising, right? So like your Coca-Cola, hypothetically, no affiliation, just pictures as example. So your Coca-Cola, for example, you're like, okay, I have 5 ads, 1, 2, 3, 4, 5. We're going to be looking at exactly this example of advertising in the practical side, but there'll be 10, so make it even harder. But let's say your Coca-Cola, you have 5 ads for a campaign. You don't know which one works the best. The method that most people would use by default is A/B testing. Let's A/B test the hell out of this, find out the best one, then we'll use that one. But what if you want to save, a couple $1 million? What if you want to just throw in a UCB algorithm in there and, you just you show these ads one by one. Every time, instead of pulling a lever, you show the person a different ad. Every time they come on your page, you show them an ad, And you use the UCB to define which ad you're showing. And as you're showing more ads, you're using exactly what we walked through, and then you're showing this ad, you're showing that ad, and all of a sudden, without having to wait for, I don't know, like 10,000 steps, on like 2,000, 3,000 steps, you're like, oh, this is the best one, I'm going to exploit that. How much money are you going to save your company like that? Tons, especially if you have lots of ads that you're picking from. You're going to save tons of money, and that's what I mean when we say that you don't need to be an expert in machine learning to bring business value. You now know kind of the intuition behind UCB. You know where you can apply it. Hadelin will show you the code. You can go and try it out. That's pretty much how it works. I love this example because it's so realistic. It's so you live and breathe it. It's not just, you see it all the time. You see ads all the time. Maybe, I don't know what Coca-Cola uses or other company use, but if they're smart about it, I don't think they'd be just using A/B tests. And if they are using A/B tests, then you can come into an interview and say, hey, I can do a new UCB algorithm for you. I know what it is. So that's us for the intuition. I hope that was useful. And now we're going to do the practical side. Hopefully you'll have question time at the end.
All right, so now time for the second challenge. So the second challenge is about finding the right ad that will lead to the maximum sales, and that is called click-through rate optimization problem. So let me get back to Python. Here we go. Of course, restarting the kernel. All right, and now we're going to go to reinforcement learning. We're done with classification. And before we apply the UCB model, what we're going to do is do random selection to have a baseline model and to see what we have to beat. So first of all, what you notice in this code is that it's much shorter, and that's because the data preprocessing phase is so simple. There is actually no data preprocessing. We just import the data set, and that's what I'm doing here. So we're going to import the data set. I'm going to explain what this is about, because this is quite special. Actually, in our course, I got a lot of questions about this data set. It's not very intuitive the first time. So I'm going to Variable Explorer to open the data set. And here we go. That's the data set. So first of all, the columns are the 10 ads we want to test. So we have 10 ads of this SUV car, and we are trying to know which ad will sell the best. So for example, that's obvious that if you have an ad of a car next to a trash, it will sell less good than an ad with a car into a beautiful road in a mountain. So that's why there is this best ad that we need to look for. And as Kirill said, we need to find the right strategy to find this ad as quickly as possible to optimize the revenues and not to spend too much money. And then that's where there's the difficult part to understand. The lines correspond to the users. So to explain this, we must start with what we would do in real life. In real life, what we would do is that we would put the ads on the social network, and then when each user connects to his account, well, he will click yes or no on the ad. And actually, the lines are the event, the sequence of events where each user connects to the account. And each time it connects to the account, either it will click on one of the ads we show to the social networks, and that in this case we get a reward equal to 1. And if it doesn't click on the ad, we get a 0. However, we're showing each time just one ad. When the user connects to the web page, we're just showing one ad. And the tricky thing to understand here is that, as you can see, for a same user, I can have multiple ones. So the ones are for the ads on which the user is going to click on. And the 0 are for the ones that the user is not going to click on. But we actually don't know that. So this data set is actually a simulation. It's actually what God knows. God knows that, for example, the first user of index 0 is going to click on ad number 1, ad number 5, and ad number 9. Then the second user is only going to click on ad number 9 and is not going to click on any of the other ads. And, but we don't know that, so that's why it's a simulation. And this is actually the only way we can train a reinforcement learning model with this kind of data set, simulating what would happen. But in real life, we actually don't know any of the ads the user is going to click on. So to make sure, does everybody understand what I just said, or do I need to re-explain? Is that clear? OK. So cool. So now that we have the data set, we're going to train our UCB algorithm. First the random selection algorithm, and we're going to see the total reward. That is, the number of clicks, and you can multiply this number of clicks by 1,000, and that will, for example, give you the dollar amount earned. So let's start with it. OK. So random selection, here it is. So the random selection is this code section here. As you can see, what I'm simply doing is that I'm going to go through all the users of the data set, and each time I'm going to select randomly one of the 10 ads. So just one random ad, and then I'm going to get the reward. So if the user clicks on the ad, then the reward will be equal to 1, because yes, that's the reward, because actually the user clicks on the ad, meaning that he will buy the SUV. And if the user doesn't click on the ad, we get reward 0. However, when we put an ad on the social network, that has a cost, and therefore we should not have too many zeros, otherwise we'll have too high cost. So, and then what will happen when I execute this section is that we will get, in the end, the total reward. That is, I'm going to actually show it the different ads to 10,000 users. So we're going to have the total reward after these 10,000 ads shown. All right, so let's execute this. And here we go. And now to get the total reward by this random selection algorithm, we can just go into the console, which is the bottom right screen here, and type total reward. And the total reward when we show randomly the ads to the users is 1,285. So you can multiply it by 1,000. By the way, if you don't like this ad optimization problem, you can picture yourself in Vegas having 10 arms in front of you, and you're trying to find the optimal strategy to earn your money. It's as you want. Okay, and now let's make sure that we have a random selection. This is a histogram that I'm going to plot. All right, so that's the histogram of ad selection. So of course, each ad was selected the same number of times because this was a random selection. But now, what we would like to obtain with our UCB algorithm is, first of all, a much better reward, total reward at the end, and then one ad that is selected much more than the others. And this ad has to be found very quickly in order to optimize the cost and get the higher revenue as possible. So that's what we're going to do right now. Let's train our UCB algorithm. All right, so moving on to the upper confidence bound. I'm not going to say it. Here we go. OK.
Everybody together. Restart the kernel.
OK, so importing the data set again. All right, and now time for UCB. So very quick, in the UCB, actually the strategy happens right here. First, we have these variables that we define to get the whole vector of the ad selected. We have this variable to get the total reward in the end that is going to be updated at each round. That is when each user connects to the social network. And then all the strategy happens in this for loop here, this double for loop. And as you can see, so here I'm computing the average reward as the sum of rewards divided by the numbers of selections. So that's a first element of the equation. Then I'm calculating the delta, which is another element of the computation. But these two elements are to compute the upper bound that it will be reduced. And it is the average reward plus this delta. And by computing this upper bound, well, we will take the ad that has the highest upper confidence bound, and that will be the ad that will be selected at each round. And based on the result, whether the user is going to click yes or no on the ad, then this upper bound will be updated at the next round. So maybe at the next round, the highest upper bound will be different. And so therefore, another ad will be selected. So that's where it happens. And then I'm updating the variables, the ad selected vector, and the total reward in the end to get the total reward over the 10,000 rounds. All right, so let's do this, and let's hope we get a better reward than 1,200. I think that was something like this. So I'm going to execute. Here we go, and now we have our total reward. Let's see what it is. So total reward. And it is almost the double, 2,178. So that's definitely a click-through rate that is optimized. And actually, we can even do better with Thompson sampling. Thompson sampling can beat the UCB. Not by, it's not like we're going to triple it, but it does better than 2,178. OK, so if you're in Vegas, you're an even reacher, so that's good. And now when we visualize the results, what do we get? Well, we will get one ad that is selected much more than the other, and that's the winning ad. That's the ad that we have to show to the users to optimize the sales of this SUV. Here we go. As you can see, very quickly, the UCB found the right ad to show to the user. That's ad number 5. Number 5 because the indexes start at 0. So index 4, but ad number 5. And literally, it dominates all the other ads, and that's the ad that we have to show to the users. So that's a pretty cool problem. And if you are more interested about reinforcement learning, in our course, we also implement Thompson sampling. And you're going to see that literally with Thompson sampling, the right ad is found very quickly, and all the other ads are non-existent. All right, so hope you enjoyed the practical applications.
Yep, so there we go. We have 10 minutes for questions. Everybody, if you have any questions, let us know. Put your hand up, we'll ask. OK, Frank, right?
Hadelin, how did you pick when you split the training set and test set? How did you come up with that percentage?
OK.
Repeat the question.
Sure. So the recommended percentage in general is 80-20. So you want to have enough data on your training set to have a good training of your model, and 80% is a good proportion. And then you test your model on new observations, which represent 20% of the original training data set, and that's enough to get a relevant accuracy.
Yep.
Earlier you were drawing this circle to
Yeah.
how do you optimize the radius of that circle?
That's what the algorithm needs to do in the code itself of the algorithm. That's what it does. So you need to look more into that. That's what we omit in the intuition side of things. There just is a circle for us. Program software.
Spider. Okay, so I trained the algorithms, the machine learning algorithm on scikit-learn. With scikit-learn, you can use it on several softwares. So this is Spider, and this is an Anaconda. So I highly recommend to download Anaconda first, and then you will have the choice between Jupyter or Spider. Jupyter is better to write some research papers because you can code some LaTeX also next to it. But Spider is like a studio, so you have your code, your variable explorer, you have your console, you have everything, good tools. It's very practical. So that's Spider.
All right, let's just quickly wait for everybody to leave who wants to leave, and then whoever wants to stay and ask questions, you're welcome to, so that there's no mess going on. Let's just give it a second. It's totally fine. Yeah, so hopefully you guys enjoyed this and had fun. Thank you very much. Everybody's going. Thank you. Thank you. Appreciate it. Thank you very much. Yes, we were talking about this because I flew all the way from Brisbane, Australia. It's like a 24-hour flight to get to this conference. Hadelin flew from Paris, like a 9-hour flight, and we're like, we gotta get people excited about machine learning. That you can I hope the takeaway for you guys was that you can apply machine learning without being an expert. You can drive value. It's like driving a car without knowing how the car works underneath. Everybody can drive a car. Everybody can learn to drive a car. Not everybody can be a car mechanic, but everybody can learn to drive a car. So don't be afraid to go out there and change the world. That's our mission to bring machine learning and this stuff to you, very accessible. So hopefully you guys who's still sitting, you're locked in to the Q&A. Don't get up. We're gonna take a few more questions. Yes. Slide. Yep. Yep. Oh, okay. I might have maybe pronounced it, said it incorrectly, but the point here is, so let's do this. Can you see it? There we go. So what you're looking for is not the most applest apple. You're looking for, sorry guys, the most orangest apple. So the most orangest apple and the most appliest orange. So thanks for correcting. If I said that wrong, then that's the correct way. You're looking at the extreme cases, not that side, but the extreme to the boundary, as close to the boundary as possible. That's what you're looking for. Okay, cool. Yes. There's no Git repository, but what we showed at the start, so I'm going to quickly go to that slide. This is the page where you can get all the data sets and the course code, so it's free. You don't have to sign up to the course to access this page. Completely accessible. You can even Google for machine learning data sets, super data science, you'll find this page. Completely free. That's kind of our mission. We want to give as much away as we can. You can get the data sets, you can get the code here. And for all of our courses, all of the data sets, all of the templates, they're always free, always available. Just go to superdatascience.com and find the right course. Thank you very much. Anybody else? Any other questions while we're here? We've got a long flight ahead. Yeah?
Yeah, we have. Oh.
Sorry? Presentation. We were very bad. We only finished it today. So it's not on ODSC yet, but we'll send it to ODSC. And how about we set up a site? We'll set up a site for you guys, superdatascience.com/ODSC. You can go there. We'll put the presentation up there. Sounds good? Yeah. All right. Okay. Any other questions?
Yeah, we have a question over here.
Yeah. I would say so because I can't answer off the top of my head, but I know that UCB, a great example, a cool example of applying UCB is you've got a Silicon Valley or whatever, and you have these 5 startups, or 5 research facilities, and you want to know which one gives you the best ROI, and so you invest money into them separately, and you watch them as they give you money, as they grow. Yeah, if you apply it that way, I think the cost would be different there, so I think yes. Can you comment on that?
Yeah, yeah. You also have other versions of UCB. You have the combinatorial UCB, where you can basically have different combinations of your ads. For example, if you're in Vegas or selecting some ads, well, you don't have to select one ad at each round. You can add several of them. And what would be the best combination of these ads? Like, should we select 2, 3, 4, just one? So this is the combinatorial UCB, and that's an even more complex problem, but it's fascinating.
All right, more questions? No? Okay, yep. Sorry, high dimension?
High dimension, so n-dimensional or
Yep.
count naive base, since you're always comparing to
Yeah, so the question is from our wonderful MC here, high-dimensional naive Bayes. All the examples we give are kind of like very simplified. So 2-dimensional naive Bayes is what we're looking at. The only difference is the circle that we're drawing becomes the Euclidean distance. And at 3 dimensions, it's a sphere. In a 4 dimensions, a 4-dimensional sphere, and so on. So it's just like harder to imagine. But if you think of the points not as points but as vectors, then it all like just simple math or like high school math that's happening in the background. But it's just harder to visualize. That's why we give these examples of 2 dimensions and sometimes 3 or 1 dimensions. Yep.
Yeah.
Okay, thanks. Anybody else? Yep.
So I didn't quite hear if this was answered earlier. You sort of gave an answer that sounded like it, but I didn't hear the question. For the circle,
Yeah.
is there a theoretical basis behind the actual diameter of that circle, or is it empirically determined?
It's empirically determined by the algorithm as it goes through. That's what the optimization process is. That's the whole point of, I'll get to your circle in a second. Yeah, well, there, where is it? Oh, my God, it's so long. There we go. Come on. There we go. There's the circle. So yeah, that's the whole point. One of the points of optimization. More questions? Anybody? 3, 2, do I see a hand? Do I see a hand? 1. Okay, thank you very much. We really appreciate you. Thank you, thank you.
Thank you very much.